2009 was the last time that the naked scientist was at the Cape Town Science Centre, and CapeTalk has brought him back where he belongs. It's great to be back in Cape Town, isn't it?
Does everyone know that this is the advanced accountancy lecture? Did you know that? Just checking. I keep going to Johannesburg, and every time we're in Joburg and we go and do events there, people in Cape Town write to me and complain. And they're really very vitriolic and angry. So I said, I will promise the next opportunity I'll come to Cape Town. So here we are.
Thank you very much. And before we go to our first question, what happened to your hand?
I blew myself up a little bit.
Does that happen a lot?
No, actually, it wasn't doing the shows at the Rand show in Joburg. It was the day before the Rand show started. And I was doing all these big explosions and things on stage, and that was making a cup of tea. It's pretty amazing, isn't it? You can detonate hydrogen, you can make all these explosions, and then you actually make a cup of tea and do that. It's amazing stuff. I went into the first aid people at the Rand show, and they introduced me to Burn Shield. Has anyone tried this stuff?
Yes.
I'd never seen it before, and it's amazing. And so there's some space technology in there too, because there's a hydrogel, which is a very, very light liquid, very, very water saturated, and it's got melaleuca oil in it, which is tea tree, which is really good at killing staph and streps, the kind of bacteria that tend to cause skin infections. So it keeps it hydrated and keeps it uninfected. And actually, it was only done 2 weeks ago, and it's almost completely healed up, because my whole hand was almost a complete blister.
Oh, wow.
So A, they did a wonderful job, and B, they introduced me to some amazing medical technology.
I would buy you a glove, like one of those...
Like Luke Skywalker.
gloves for the next time you do tea or something like that. All right, to your questions. Who's going to ask the first question for this evening?
My name is Barira. Is it true that if you chew bubblegum while studying, and if you chew that same flavor in an examination, that you will remember the work that you've studied better?
Brilliant question!
That's the best excuse.
She asked that while chewing bubblegum.
Yeah.
2.5 minutes.
The best excuse for allowing people to eat at school in exams I've ever heard of. The answer is yes, and this is what we call contextual learning. The brain makes associations between things that happen to you and things that happen at the same time as things that happen to you, and it links the two things together. So if you're chewing gum at the time when you're remembering something, then there will be part of the memory signature linked to the bubblegum chewing. And so if you do anything and try and learn something at the same time, there will be a degree of pairing of the information, so you can facilitate the recall by doing the same thing in the exam. So if you happen to find that riding a unicycle helps you to revise, you may struggle to remember those things in the exam unless you do your exam on a unicycle. But yes, bubblegum, you probably get away with that.
I just want to know why I've watched waves, and I've noticed there would be no foam deep into the sea, but as it gets to the shore, there would be this white foam. What causes that?
Okay,
and why there and not deeper as the waves start forming already?
The foam you're seeing, or the spume, is caused by protein material and surfactant material, which reduce the surface tension of water. Water is naturally a very sticky molecule, and it's impossible for it to form bubbles because the molecules are trying to pull themselves together. But when you add things which are proteins and surfactants, and that's how detergents work, it reduces the attraction between the water molecules, enabling you to form bubbly stuff. Out at sea, your eyes aren't capable of resolving if there's very much foam about, and also there's less breaking waves because there's less turbulence. And so what you need is a combination of a wave or some turbulence, a rough surface for it to break over, and basically introduce air into the water, and then the water, full of these surfactant proteins and things made by plants and other animals, forms a bubble. So you tend to form more bubbles where there's more rough water, and there'll be more rough water near the shore.
And something completely unscientific, in Xhosa, that foam is called umlungu. So and we refer to white people as abelungu because they came by the ocean, and that is
I didn't know that.
Nothing to do with that.
Is the speed of light faster than the that your brain gives your body messages to move?
I guess you're asking, does the information that goes from your brain to your hand travel faster in your nervous system than light travels? And the answer is no. Information travels down a motor nerve cell, which are the big fat nerve cells that go from your spinal cord to a muscle, at about 50 meters per second. Light travels at 300 million meters per second. So light is considerably faster than nerve signals.
Hi, my name is Micheline. I wanted to know about the Wi-Fi. Lately I've been reading quite a bit on the internet and in the newspaper about the dangers of Wi-Fi and so forth. So I wanted to know, what is the technology behind it and why is it so dangerous?
This is a very controversial area. Is Wi-Fi safe? Who's got a cell phone here? Oh, put your hand up. Okay, who uses Wi-Fi on that phone at home? Right, so pretty much 100% concordance there, and 3/4 of the audience. Those are using microwaves. Wi-Fi and mobile phones are using microwaves, which are part of the electromagnetic spectrum, which is effectively light, but it's a form of light you can't see. Now, the argument is that this form of light doesn't have enough energy in the wave when it gets into your body to break chemical bonds. Because if we look at the kinds of light or electromagnetic radiation that do you harm, these are very short wavelength, high frequency, and therefore high energy forms of waves like X-rays, gamma rays, and ultraviolet. When they penetrate tissue, they make bonds between atoms jiggle sufficiently hard that they can actually break those bonds. And if this happens in your DNA, you can rearrange your DNA and introduce what are called mutations. Microwaves do not have sufficient energy to do that. So the argument is that this should be biologically safe, and there doesn't appear to be any strong evidence that if you expose tissue, living tissue, to these sorts of signals at the sorts of intensities that we're being exposed to them, that there is evidence for things like cancer. That's not to say there couldn't be a health effect, because you could be exposing yourself to this radiation and warming up your tissue, and it might be that the thermal challenge has a health effect, because you are cooking your leg with your mobile phone in your pocket, and you're cooking your brain with your mobile phone held to your ear. So at the moment we don't know, and nature, the world, is doing a massive great epidemiological experiment where there are something like 7 billion mobile phones being used on Earth right now, and the same number of Wi-Fi devices, and we're all being exposed, and for the first time in history we know how much, because phone companies know exactly how much you're using your handset, whether you're sending or receiving calls. There's one coming in. And so we don't actually know yet whether there's a link, but ultimately, in the long term, we will.
I'm originally from Gauteng.
You poor thing.
In summer, when it rains in Gauteng, or any time when it rains, you know, you get thunderstorms. And after the rain, you get a rainbow. Whereas in Cape Town, there's hardly ever a rainbow after the rain, and it rains in winter, and there are no thunderstorms. So I know it has got to do, I'm assuming it has to do with the mountains and the sea, but I need to
well, what's the recipe for a rainbow? That's a good sort of way of putting the question. And to have a rainbow, what you need is rain, and you need sunshine. And what happens to make a rainbow is that sunlight, which is white light, and white light is a mixture of all of the colours that we can see, and when all of those different colours hit our eye, what our brain says we're seeing is white. When that white light goes into a raindrop, when light goes from one medium, air, into another medium, which is water, it bends a little bit. That's called refraction. And so all these different colours of light bend by slightly different amounts inside the raindrop. They go across the raindrop and bounce off the inside back surface of the raindrop and reflect back out towards you. And they then bend again a bit more as they come back out of the raindrop. So your eye sees all these different colours of light coming to you from that patch of the sky. And that's what actually makes the rainbow. In order to see it, you're going to need a rainy backdrop. I mean, it's not true that there aren't rainbows in Cape Town, because I was at Cape Point 2 days ago and I watched a beautiful rainbow form in the clouds that were coming up off the ocean over Cape Point. So I think the reason that you probably see fewer of them is if you don't have as many rainstorms as you do in Gauteng, because when
Yes,
it rains there, it really rains.
Rainstorms and the rainbows are scarce. Whereas in Gauteng, it's something. Once it's rain, you know it rains. You know you're going to have a rainbow, and there'll be so bad. There's
Probably a combination of factors, but basically the same physics is going to apply. And as long as you've got a nice dark sky that's going to send the light to you, you'll get a nice rainbow.
The thunderstorms.
Anything that's a water-laden sky can make a rainbow.
I'm not sure you are hearing me. What about the thunderstorms?
So you're asking why Joburg has thunderstorms and Cape Town doesn't?
When it rains, whereas here it just rains, there are no thunderstorms. There's also the scarcity
a thunderstorm is just a very vigorous storm when there's a lot of energy in the atmosphere. And what happens is that you get warm ground, which makes warm air, and it evaporates water up into the air. The air rises very quickly, and it then condenses, because as you get air rising, it also feels less pressure, so it expands, and when it expands it cools, and cold air can't carry as much moisture as warm air can, so cooler air therefore condenses out its moisture into lots of droplets, and it happens very quickly all at once. And you have this huge storm cloud with lots of water in it, so then it rains extremely hard, and those water droplets, or the hydrometeors, the little ice particles in the cloud which are bobbing up and down, are effectively like you rubbing your hands together or rubbing a balloon against your head. They make friction between the particles and separate charges in the cloud, which is what makes the lightning happen. So a big storm can make thunder.
Which makes sense because in Joburg you've got summer rains, whereas in Cape Town we've got winter rain, so the ground is cold as opposed to Joburg that has hot ground. Thank you very much for your question.
I often watch a sitcom called Big Bang Theory, and they often talk about string theory, and I don't know what they're talking about.
Neither do they, don't worry. Well, string theory is a theory. And the whole idea of this is that you've basically got, we think of, how do I put this? Right, we need to think of the existence of multiple dimensions. And these dimensions can all be resolved to strings. And these strings can vibrate. These one-dimensional strings can vibrate. And so when you think of an atom as a string with a vibration, and that vibration corresponds to some of the particles that make up the atom, that's basically one theory of how matter works, string theory. But it's just a theory, and there's no evidence to actually support whether or not it's true. It's just a construct of physics to explain some of the aspects that we see in our model of the world around us.
And it was constructed by people in physics as opposed to Hollywood writers of the physics?
No, it's genuine theoretical physics, but as a theoretical physics friend of mine said, that with maths you can prove anything you like.
True.
So what tends to happen is you have a theory, and this enables you to make predictions, and you then go to test those predictions based on real-world observations to see if your predictions are borne out. And then you can say, well, my theory appears to work, so I think probably this is what's going on. So this gives us some answers to some of the things that we're trying to explain in physics.
How does an EMP work?
An EMP?
Electromagnetic pulse.
Right, okay. The whole point of this is there are lots of devices, including your own body, which are electrical. Your brain is electrical. My phone on the table is electrical. And magnetism and electricity, as Michael Faraday showed, are linked. And so if you create an intense pulse of say, a magnetic wave or an electrical wave, you will then induce a current to flow in anything that can sustain a current, and this can be disruptive to the functioning of that thing, whether that's a living tissue like your brain or a device like a mobile phone. And so people are talking about you could use this as a weapon, for example, because you could create a very intense pulse of electromagnetic energy, and this would then have a disruptive effect on devices and send big currents through them.
All right. Out of interest, why is it that sometimes I will walk past you and then I would send out shoots of electricity, but then when I walk past her, I don't?
Show electromagnetic personality, I suppose.
Perfect answer.
No, actually, it depends what shoes you've got on and even what pants.
Really?
Because when you have materials rubbing against each other, if they're not conductors, then actually you can transfer charges asymmetrically between surfaces. And if you've ever done the experiment where you rub a balloon on your head and it will then stick to the wall, what you've actually done is to transfer some negative charge onto the balloon. So the balloon surface has a net negative charge. If you bring the balloon close to the surface on the wall, the electrons in the wall, which can move, will be repelled by the electrons on the balloon, which can't move because the balloon isn't the conductor. So as you bring the negatives close to the wall, all of the electrons in the wall scatter away, leaving the positive charges, which are then attracted to the negative charges on the balloon sticks. Now, because of that build-up of static electricity, if you're walking around with a charge on you and that you then touch somebody else, because there is a surfeit of charge in one place and not in another, nature abhors the fact that there is this disequilibrium. So some of the charge tries to flow to balance things out. So you can give someone an electric shock. And actually there are a big excess of people in America having fuel tank fires in their cars. And when people looked at CCTV footage at garages where people were filling up their cars, they noticed that lots of people who were victims of their car fuel tank exploding while fueling were women.
Wow.
So then they said, well, let's have a look at what women do. And in America, you can lock off the fueler. So you put it in, lock it off until it fills the tank, and then it automatically disengages. People would put it in and then wander off. And because women don't tend to have wallets in their pockets, they would have handbags in their car. They would then get back in their car, slide across the seat, especially in their slinky trousers or pants or whatever they were wearing, and asymmetrically transfer some charge onto themselves. Then they would get out, now armed with their handbag or purse, go around and take the fueling nozzle out, but by then they've now got charge on them and touch them and it goes zap. And the fuel vapor that's come out ignites and you get a flash and then you light your fuel tank. So don't wear nylon undies, ladies. Cotton pants only.
All right.
My name is Emma, and I would like to know what is under a black hole.
Well, first of all, what's a black hole?
Yeah.
Well, a black hole is a patch of space which has an extremely intense gravitational field around it, and that means it must have a lot of mass and matter inside it. But it has such an intense gravitational field that it has crushed matter so that matter no longer exists in the form of the stuff that we're made of. We don't know what's inside a black hole because black holes have such a powerful gravitational effect that they distort space to such an extent that not even light can get out of them, because the black hole sits in space and it bends space around itself, so when light comes through, the light goes into the black hole and can't come out again. So we can't look into a black hole in the same way that you can look at a star with a telescope. So that's why the discovery of gravitational waves recently was really important, because it gives us a new way of looking at how black holes behave, so we can begin to answer that question, because no one knows what's in there.
And will the square kilometre array help in any way in trying to come up with those answers?
Well, the square kilometre array actually will enable us to look at the universe in quite a different way, because that's going to look at radio waves and that kind of thing, but it will do it on such a massive scale because the array is 3,000 kilometres across. So what you're doing is building a telescope like a collecting dish 3,000 kilometres wide. So rather than just one satellite dish that we have at the moment, you've got one which is huge. And if you collect that much information from that far across the universe, then you have an opportunity to actually resolve the direction that waves are coming at. And you can get a much clearer picture of what made those waves. But they're not looking for gravitational waves, they're looking for radio and sort of electromagnetic light type waves.
Hi everyone, my name is Jamie. I would like to know what is the function of the appendix?
Well, the appendix is also called the vermiform appendix, and it sits on your cecum. So if you were sort of looking at me, this is where my large intestine is. So cecum here, transverse colon there, descending colon there, sigmoid colon there. The cecum is a big bag, and it's connected into by the small intestine, and hanging off of it around the back is the vermiform appendix. It's about that long, and it seems to be a lymphoid organ. What that means is, if you look inside it, you find lots of collections of B, which are white blood cells, which are also snuggling up to another form of white blood cell called a T cell, which appear to be educating each other, and perhaps educating the rest of your immune system about what's in your food and what you should and shouldn't be reacting to, and what you should be tolerant of. So don't have an allergy, or don't react to certain forms of food, but do react to other things. It appears to be of low importance because, as anyone who's had an appendicitis When we remove the appendix, because it becomes inflamed, those people appear to be completely healthy afterwards. There doesn't seem to be any immune consequence. So we believe it probably plays a role in educating your immune system, but because you've got lots of places to educate your immune system, you can do without it.
Hi, my name is Darren. I can't remember what the name is, but with the large satellite that you speak into, when I spoke into it softly and my grand could hear it, when she whispered back into it, I could hear it. How is that possible?
Are you referring to the two dishes, which are a big distance apart? You whisper into one and you can hear the sound in the other one. Well, if you look at the shape of that dish, it's a very clever, crafty curve called a parabola. And in the same way that when you hold a magnifying glass up to the light, it brings light to a focal point, it's the same shape. It focuses sound, so when you speak, you put vibrations into the air. They are captured at the mouthpiece, they go towards the dish, they are focused by the dish into a parallel running set of waves which run to the other dish, which then reflects them back to a focal point where the person puts their ear. So you're basically capturing sound waves over a very big area, sending them in parallel to the other dish, and that then captures the energy over another big area and focuses it back to where your ear is so you can hear it. So you can imagine you could do the same trick with light actually. If I had a very bright light where you put your mouth to whisper, then I had a shiny surface, not a white surface. At the other side, I could then pick up a very, very bright light. And you can actually do this. We've got some parabolic reflectors. We've done an experiment where we put a Bunsen burner at the focal point of one of the dishes and some explosive at the focal point of the other dish, and you can light the Bunsen burner and make the explosive go off yards away.
That is so cool. That is actually so cool.
Well, it's actually quite hot, but yeah.
I can imagine.
I would like to know whether cell phone towers can affect the migratory parts of animals, like birds, for example, and can they be the reason why bees are having such a big problem?
As a part of the context, in the Western Cape, we've got a particularly bad bee situation, which obviously means that pollination is becoming a challenge and so forth and so forth. Just a bit of background.
Yeah, this is a global phenomenon. It's broadly referred to as colony collapse disorder, or CCD. And it was first really documented about 10 years ago that bee numbers appear to be in decline, but no one seemed to know why. Current evidence suggests that it's multifactorial. We don't think there's one single cause. There's probably a range of different challenges facing bees. One is that there is exposure to insecticide and other environmental things. 2 is possibly a change in climate. 3 are parasites. We know that bees are succumbing to things like varroa mites, which are these little, they're effectively like you getting nits or fleas. These things hitch a ride on bees, they drink the blood of bees, but there's now evidence that when they do that, in the same way that mosquitoes can give us malaria, these varroa mites can infect the bees with various viruses, which then debilitate the bees. And because the bees are already under pressure, it's the straw that's breaking the camel's back. The other thing that's being highlighted is that the bees are very often taken to areas subjected to pollination of a monoculture, so they just end up with millions and millions of fruit trees to pollinate, nothing else. So rather than making a honey which is rich in a whole range of different pollens and nectars, they end up with a very, very sort of monotonous diet. The farmer then nicks most of their diet and gives them sugar syrup, which is of low nutritional value to bees to drink to get them through the winter and to replace the honey they've taken away. And it's leading to a progressively less fit bee population, which are now succumbing to more infections and more challenges. And so it's probably not just one single cause that's causing this.
But can cell phone towers though cause?
Not really. As we were saying earlier, people are looking at this, but there's not really any evidence because we've got really good data on where these towers are, how much radiation they're putting out. In Israel, they've got a project to look at rainfall using cell phone emissions. Because microwaves get absorbed by rainfall quite strongly, you can use how much energy Vodafone have to put out to keep their cell phone active. And so you can say, well, we know how much rain there is in any given area of the country based on the cell phone power emission. So they're logging all this data, but there's not really any consistent evidence linking it to any one outcome, like human or animal.
Hi, my name is Hawa. My question is for my kids. They are really tired of finding X, and they feel that maths in high school is an absolute waste of time. So I want you to explain to them how the intricacies of maths will actually help them in later life or in adulthood.
No, I absolutely agree with you guys, because I remember sitting in a maths lesson and there was a friend of mine sitting at the desk opposite and he said, So what is the point of integration? And what am I going to do? I'm going to be walking down the street, I'm going to see a tree that's been differentiated, so I have to integrate it to put it right. Is that the point? And you know, everyone sort of thought it was a bit nuts, but it's true. It's very hard sometimes with some aspects of maths to see what the relevance and what the point of it is. But the point is that there is no aspect of science that doesn't in some way get informed by or rely on maths. And I'm so glad that my parents put their foot down and made me suffer, because in the long run, actually, I became much better at maths and I understand a lot more about how physics works and chemistry works and biology because I did maths at a higher level. And understanding the physical relationships between numbers is very, very important, and there is no science that doesn't depend on it. And you can also add up what your bill should be in the supermarket, which is pretty
true. Very true.
Hi, my name is Jason. I want to know what your opinion is on the multiverse theory.
Okay, so are we part of a multiverse or is there one single universe? The answer is there are a whole lot of theories, and there's a very good book by a guy called Michio Kaku called Parallel Universes, and what he's contending in his book is that there are multiple universes, we're unaware of their existence. They could be hovering just millimetres in front of your face and you're there in another science centre listening to another bloke pontificate about science, but you've no way of knowing that you're there. What we do think though is that gravity might exchange or pass between these multiple universes, and one way to detect and test this is to look for gravitational waves, which is why things like the LIGO experiment are so important, because if multiple universes do exist, we may be able to find them. People also say that at the arse end of a black hole, there may well be a white hole, which is a big bang in a new universe, in a new parallel universe.
Why is it important for us to know? Like, is it not enough that it's a Thursday afternoon, it's about 6:45, and it's a beautiful gathering of people asking questions? Like, do we need to know that there are other universes that exist on the other side?
Who would like to know if there is life elsewhere in the universe?
Question answered. Thank you.
It doesn't matter, but it's pretty important, isn't it?
Yeah. Oh, sorry. Out of interest, are there other? Do we know there are other like beings who are also trying to search for us?
No, we don't know whether they're there, and if they are there, perhaps they just took one look and went, "We should just steer clear."
I like it.
Good evening. I'd like to know, could you explain how quantum computing works?
I can try in 60 seconds, but this might be difficult. Although if I speak really quickly, because of relativity, time will slow down for me, and so I might be able to pack more in than I thought. The answer is that with traditional computing, we work in binary, noughts and ones. There was some computing going on right there. And what that means is that you're constrained with how much you can do in parallel. But quantum is a grayscale. You can have every possible thing between black and white, naught and one. And so the idea here is that actually you could do a huge and furious number of different calculations all in parallel all at once, because you can have all those different values, not just a 1 or a 0. And so people are also saying, can we now build computers which work with light, channel light through the computer, rather than an electrical signal, because electricity generates loads of heat, and you begin to get quantum effects when you make the transistors at the tiny scale that you're making them now. You begin to get interference between them, and it becomes tricky. If we could actually use light, you wouldn't have to use this huge amount of energy. Your computer wouldn't use more electricity than it does to run your bath. And I've run out of time.
And then my last question is relating to cooking. I love cooking.
Yeah.
And I am a total believer in taking a piece of protein, for example, seasoning it beautifully, adding a splash of wine if you choose to, putting it in the oven, and then forget about it for a couple of hours.
Yeah.
Because by slowly emitting, I suppose, penetrating heat into it, the muscle just slowly lets loose, and what you taste is going to be so much more flavorful.
Mm.
And yet we live in a generation, I suppose, that needs something zapped in 2 minutes and ready to cook. Are we ever going to get to a point where technology develops that we can have something in 2 minutes, but have it as beautiful and succulent as if it'd been there for 8 hours?
Well, it's sort of boil in the bag does work a bit that way, actually, because what you do is you make the food and you then marinate it effectively, and you let all those flavours work their way in. And most people probably know if you cook a curry, It tastes good the first day, but if you put the curry in the fridge and then have it the next day, it tastes bloody fantastic.
That's right, yeah.
And that's exactly why, because the flavours all get suffused into the meat, and there is that sort of exchange. So I think perfectly possible, yeah. Cooking is just chemistry, effectively, and it's knowing how to play with the chemical reagents that you're playing with to get the chemical reaction to go the way that you want it to go, and that's what the good chefs are good at.
And that's why you must study mathematics so they can cook better.
You can weigh out the ingredients.